Okay, hi everybody, happy Monday. This is lecture 16. This is our third and final lecture on differential equations, but you'll be seeing them tomorrow in recitation. I'm going to do three things today. Last week there was a lot of talk about differential equations, but very little actual solving. I showed you solutions that the book had come up with. I think I might have solved one or two, but I just want to give you, another. We'll do a little harder one. So example one for today is, so this is solving diff EQs, and see the book for various examples. It's a hodgepodge of things that you'll have to do for different kinds of problems. So example one is similar to 7.7 number 13, which is one of your web-assigned problems. So find the solution to the differential equation. So find the particular solution to the differential equation y prime cotangent of x equals a plus y. That satisfies the extra condition that y of pi over 3 equals, I'm going to say 5a. So we start by finding the general solution. To this differential equation, y prime cotangent y equals a plus y. Now, can any, before we do any work here, can anybody, yeah?
Is that cotangent of y or
cotangent of x? Thanks. Can anybody think of any constant solutions? That is y equals c. Or maybe I'm going to say k for constant. Constant with a k. Can anybody think of any functions that are of the form y equals k that satisfy that differential equation? Raise your hand if you can think of one. If you had a constant solution and you plugged it into the left side, what would happen to the left side? Let's get some more hands up. What would happen on the left side if y was a constant? I want to get about 5 hands in the air. Liam?
The derivative of a constant is 0, so the left side would become equal to 0.
The left side would be 0. So if the equation is going to be true and the left side is going to be 0, what's going to happen on the right side? Exactly. The right side's going to have to equal 0 as well. So y equals minus a is a solution that's a constant. Okay, well, that's important to know because, you know, we've got one solution. Could that be the one we're looking for? Let's look ahead. Let's, you know, let's not get too spooked, but you're shaking your head. Why?
I don't know.
Well, you were right. You should go take the win. You know, that constant solution, y equals negative a, what would be its value when x equals pi over 3? It'd be negative a. It's the constant function. So that's not going to satisfy our extra condition. That's cool. So we've already found one general solution, but it's not a good one. But let's go on. Look for other general solutions. So let's take our equation and let's divide by, so let's assume that y is not equal to negative a. Well, then a plus y will not be 0. Again, we already found that y equals negative a is one solution, so we're going to look for other ones. So since a plus y is not equal to 0, we can divide by it. Divide both sides by a plus y. So I get 1 over a plus y, and then I've got a cotangent of x dy equals 1. Oh, is it dy dx? Sorry. And let's divide both sides by cotangent of x. So on the left side, I get 1 over a plus y times dy dx equals 1 over cotangent of x. Now, what's 1 over cotangent of x?
Is it sine?
Tangent. Cotangent is just, it's the co of the tangent. Okay, then let's put this in differential form and integrate. So I get 1 over a plus y dy equals tan x dx. So when I integrate, I get integral of 1 over a plus y equals the integral of tan x So when I do a u substitution here, so this is the integral of sine x over cos x. So when I do a u sub, I let u equal cos x. Then what I've got there is minus du. So in other words, du dx is minus sine of x. So what I end up with is minus 1 over u du on the right side. And on the left side, I get ln of absolute value of a plus y plus c1, where c1 can be any real number. So this is going to be minus ln of absolute value of u plus C2, some other constant. And then we plug back in what u is. So ln of absolute value of a plus y equals minus ln of absolute value of cos x plus C2 minus C1. But C2 and C1 could be any real number. So C1 and C2 can be any real number. So if they have the capability of being any real number, then C2 minus C1 also has the capability of being any real number. So I can write this as minus ln of absolute value of cos x plus some number C3, where C3 is any real number. So ln of absolute value of a plus y on the left. So let's raise e to both sides. So e to the ln of absolute value of a plus y equals e to the minus ln of absolute value of cos x times e to the C3. Because remember, e to the a plus b is e to the a times e to the b. So I get absolute value of a plus y equals, now when I take e, remember that a to the minus b is the same as 1 over b, and 1 over a to the b. So e to the minus ln of b is going to be 1 over e to the ln of b. So that's going to be 1 over b. So on the left side, when I take e to the ln of this stuff, I just get that stuff. Over here, though, I've got e to the minus ln of that stuff. So what I get is 1 over absolute value of cos x times e to the C3. Oh, and I'm going to say here C times C4. So C3 can be any real number. Could be 1 billion, could be minus pi, could be 3.5. But what about e to the C3? What could it be? If C3 could be any real number, what could e to the C3 be? Marcy's got a hand up. Anybody else? 2 hands up, 3 hands up, 4 hands up. Cassidy? Not quite. Marcy?
Any real positive number?
Any positive number. Remember, e to any power is always positive. So C4 is any positive number. Because remember, the graph of e to the x has an asymptote on your left and it goes up on your right, but the whole thing lives above the x-axis. So e to anything is always positive. So c can play around all at once. It can be any real number, but you feed that into the exponential function, and you're going to get something which is positive. Now, what about those absolute values? What's going on with that? Well, normally, if we know something is positive, we can chuck the absolute values. If we know something's negative, we can just chuck the absolute values and put a minus sign on the thing inside. But if we don't know, well, shoot, then we're kind of stuck. So all we can say is that a plus y is equal to plus or minus 1 over cos x times C4. Because this thing might be positive or negative, so if I take the absolute value signs away, it might incur a plus or a minus sign. This thing might be plus or negative. So the left and right sides, we don't know that they're equal, but we know that they're equal within a plus or minus sign. So that means that y is equal to minus a plus or minus 1 over cos x times C4, where C4 can be any positive number. Could C4 be 0? Well, no, I just said C4 has to be any positive number. But look, what if C4 were 0? We can't have C4 be 0 from what we just went through. But I could invent a new constant, C5, because I just like inventing constants. Because look, if this thing were 0, y would be negative a. That's actually one of our allowed solutions from over here. So here we found the y equals negative a is a possible solution. And then here we found all the solutions that are not that one. So in general, combine those two general solutions. So C4 could be any positive number, but then plus or minus C4 could be any number that's not 0. But then we found out over there that if this term were 0, that'd be okay as well. So we can just say that y equals minus a plus C4 over cos, C5 over cos x, where C5 can be any real number. That's our general solution. My handwriting says general solution. So again, one of the general solutions was the one y equals negative a. So that's all. Finding the general solution. So the general solution is circled. Now we have to satisfy the extra condition. I'm going to do that over here. Now the extra condition was that y of pi over 3 equals 5a. I'm going to turn that around. 5a equals y of pi over 3. So what's that? Well, it's minus a plus c5 over cos pi over 3. Anybody remember what cos pi over 3 is? Who knows? Some more hands. Andrew.
Isn't it 1/2?
Yes, it's 1/2. So this is minus a plus c5 over 1/2. So that's minus a plus 2 c5. So let's figure out what c5 is. So that means that 6a equals 2 c5. So that means C5 has to be the number 3. So the particular solution well, yeah, 3a. The particular solution is y equals minus a plus 3a over cos x. There we go. Notice that's not a constant solution. There was a constant solution that was a general solution, but it's that particular constant, that particular solution, y equals negative a, is not a particular solution that satisfies our extra condition. So there we go. That's meeting part 1. Meeting part 2 is called direction fields. So the idea of direction fields is this. Sometimes dy dx, well, when dy dx is presented in the form dy dx equals some stuff involving x and y. So on the right side of the equation is, both x's and y's. It can be useful to visualize dy dx in this way, in the following way. So visualize it in the x, y plane as follows. At location x, y equals a comma b in the plane, put a little miniature tangent line that indicates the size of dy dx at that point. This is a little mini tangent line. To indicate the direction and size of dy dx there. That sounds really vague, but I'm gonna do this anyway. Just gonna plow right on. So for example, so here's our second example for today. Consider the differential equation. So diff EQ, remember that stands for differential equations. So consider the differential equation y prime equals x minus xy. Oh, sorry, x minus xy. So A, sketch a direction field. So draw a direction field. For dy dx. So that's question A. Now direction, so dy dx of course is just y prime. So first of all, let's present this in a more helpful form. So dy dx is going to be x times the quantity 1 minus y. So that's just the factored form of this. Now, let me ask you, so this is going to depend on where you are in the xy plane. If you're at 5, 7, you'd put 5 in for x, you'd put 7 in for y, and you'd get that the slope is minus 30 at that point. So at every point in the plane, you're going to have some number that's the slope, and we're going to plot those as little mini tangent lines. So here's a question for you. Can you spot any patterns in that differential equation? Any values of x or of y that are going to cause the slope to always be 0? Good. Yeah, so observe when x equals 0, the slope is always 0. M equals 0. And also when y is equal to 1, the slope m equals 0. So let's just go fearlessly first. That was actually, for a while, we had a slogan. I think there's a very large building somewhere on the OU campus that's full of people that think of slogans for OU. For a while, we had a slogan that was fearlessly first. So here we go. Fearlessly first, we're going to make our slope field. So we've just figured out that when x is equal to 0, the slopes are always going to be 0. So raise your hand, where on this plane are the locations where x equals 0? The y-axis. So all these places where x equals 0 are on this y-axis. We have to convey the fact that m equals 0 there. Well, that means that you'd have a horizontal tangent line. So you basically got a set of kind of red Venetian blinds here on your y-axis. At all these points, the slope has to be 0. Where are the places in the plane where y equals 1? Too slow. It's the line, y equals 1. So here is y equals 1. So all along this line, we also have to have little horizontal tangent lines. So that's the beginnings of our direction field. You see, at each place, we've got a dorky little thing which is supposed to represent the direction of the tangent line. And the steepness of the line gives you this an idea of the size of dy dx. So notice when x is equal to 1 and y is equal to 1, we're sitting right here. What's the value of the slope at that point in the plane? Marcy?
0.
0. Now what about when x is equal to 1 and y is equal to 2? Somebody else. What's the value of the slope here? Yeah. Negative 1. So there, my slope is going to look like that. What about when I go up to 1, 3? Well, the slope is going to be 1 times -2, so it's going to be steeper, twice as steep. And when I go up even farther, the slope is going to be even steeper still until my hand explodes because these are so steep. Now, what if I go down? What about at 1, 0? Somebody new. What's the slope of the graph at 1, 0? 1. So, and as I go down, the slopes are going to get steeper. Now, what if I flip this over on the left side? -1, 2. What's the slope there? Marcy, what's the slope at, I think that was your answer there. So what's your answer here? What's the slope there?
-1.
Nope, it'd be 1. It'd be -1 times 1 minus 2. So -1 times -1 would be 1. M equals 1. So the mirror image, because y didn't change going from here to here, but x changed. X changed sign. So this slope field is symmetric across the y-axis. And notice it's also symmetric across this red dotted line. Now what happens if I go farther out? If I go farther out on this line, I'm still at, say, y equals 2, and I go to x equals 2, then my slope, instead of being -1, is going to be -2. So my lines get steeper as I go out here on each of these So it becomes really hard to draw these things. So don't get, remember I was saying, with the solids of rotation, all that stuff, really enjoy relishing that craft. For the slope fields, don't sweat it. Don't try to make these things pretty. They're going to be ugly. They're going to look ridiculous. But the real money is observing the places where you know you have horizontal tangent lines. That's going to be the crucial thing, to recognize that trend. Okay, but I'm going to put some more of these things in here. So as I go out on any of these lines, I'm really not trying to do this very well. I'm just throwing, it's kind of a Jackson Pollock slope field. You should wear eye protection when you do this. Okay, so everybody got that. Now let's go to helpmecheatamycalculus.com and look at a slope field for this. So Desmos does a great job with slope fields. Look at that. So notice, there's our Venetian blinds going up the y-axis. All those tangent lines are horizontal. There's the horizontal line y equals 1. All along there, the tangent lines are horizontal. So, what we just went through, again, it's humiliating because you make these slope fields and they just look terrible. And in the book, you get some questions that say, make a slope field. But in WebAssign, you don't. WebAssign just says, here's some slope fields. Which is the right one? And for that, you just are going to look for clues, like where are the places where the slopes are 0. That's the key to unlocking those kinds of problems. All right, now that's question A. Draw a direction field for this. Now question B is sketch a solution, a particular solution that goes through the point 1, 0. So that goes through the point xy equals 1, 0. So the idea is that, this is at every place in the plane, this is what the tangent line would be if the graph were going through that point. But of course, a particular graph won't go through all these points at once. But if I say that the tangent line has to go through 1, 0, I'll get out my pumpkin spice chalk and we'll have a graph that's got to go through this point. Well, so that means it's got to have this as its tangent line. Okay, so that means the graph is going to have to be coming in like this. Oh, look, as it goes to the left, the tangent lines have to level off. So that graph is going to have to fly into this point that way. Now, what about as it goes to the right? Well, as the graph gets up closer and closer to that red dotted line, the tangent lines have to get shallower. So the graph is going to have to do this. And it's going to have to do this on both sides. It's going to be symmetric. Raise your hand if you have a description of what that graph looks like. A poetic one. Well, not poetic. Jace?
Isn't it the logistic growth that
Well, the logistic growth, good question. Is it logistic growth? Logistic growth we never look at for negative t. So we don't know, we've never considered the left side of the logistic growth. But I can tell you it's not. But it does look like something else that has come up in our class before. Kenzie?
Is it an upside down bell curve?
It's an upside down bell curve, it looks like, doesn't it? Of course, now we've seen things that look like bell curves that are not bell curves. For instance, 1 over the quantity 1 plus x squared. That looks like a bell curve, but it's not like the bell curve. But this looks like an upside down bell curve. hey, let's get really smart about this. So a bell curve, remember, is y equals e to the minus x squared. Maybe some constants thrown in there just to look sophisticated. So what would be upside down be? What would be the equation for an upside down bell curve? Too slow. Y equals minus e to the minus x squared. It just flips it upside down. What would be the equation for an upside down bell curve that's been moved up 1 unit? Trent? Yeah. So this looks to me like something of the form y equals minus e to the minus x squared plus 1. This will impress your parents. This is if you're trying to get permission to go to Cabo over spring break, this is what you show them. Let's go to helpmecheatomycalculus.com. And let's solve y prime equals x times 1 minus y. You know that 1 over e to the x squared is e to the minus x squared. So that's what we're looking at. 1 plus e to the minus x squared with some constants. That's what this is. This is a bell curve flipped upside down by putting it in the denominator and then moved up by 1. Isn't that cool? Yes, it's cool. All right, so there's the idea of direction fields. I don't want to belabor this, but you do have some exercises on this. You'll get some in recitation as well. All right, we have 15 minutes. Meeting part 3 is mixing problems. So last week, I talked about what a differential equation is, and then I talked about what it means for a function to be a solution of a differential equation. We solved maybe a couple of differential equations, but we also just took some given functions and checked them to see if they were solutions or not. And then we discussed the logistic differential equation, which we approached from a modeling standpoint. We had some hypothesis about how our population behaves. Its growth is proportional to the population, the product of the population, and the difference between the population and the carrying capacity. And out of that comes a differential equation. And then you solve that, and you've got a function that models your population. So here's another modeling problem. So we have a room with volume V equals 180 meters cubed. And it initially has a concentration of concentration of C, the room with two, I'm just going to spell room with just 2 O's, initially is going to be 0.5%. Now that's by volume. So for instance, if your room volume is 180 cubic meters and your concentration of CO2 is 1%, that means that 1.8 cubic meters of CO2 are in this room. So so this would mean that 0.9, so initially the amount of CO2 in the room is 0.9 cubic meters. fresh air, or fresher air is flowing in at a rate of F, the flow rate is 2 meters cubed per minute. So you've got, your room's all closed off, but there's a ventilation duct forcing air in at 2 meters cubed per minute with concentration of CO2 constant. So the incoming air is fresher, so I'm going to call it Cn, and it's 0. Oh, this is a mistake. This should say 0.15. 0.15% is what's in the room now. What's coming in is 0.05%. So fresher air is coming in. And then room air, so mixed room air is leaving at the same rate. So let's draw a picture of this. So here's our room. I don't have to, it's the room. So the volume V is 180. And we have incoming air. So the flow rate is F equals 2 meters cubed per minute. And the concentration is Cn, which is 0.05%. And then we have outgoing air. Well, the outgoing air is flow rate F, the same as the other. But the concentration is whatever the concentration of CO2 in the room is. So the question is to give a formula for the concentration of CO2 in the room as time goes on. So look, you've got a room, a bunch of people were in here breathing, they left it full of a pretty high concentration of CO2. You're pumping in fresher air. It's not pure, it has some CO2, but not as much. So what do you expect the concentration of CO2 is going to do? It should gradually go down as you're flushing out mixed air and replacing it with fresh air. Eventually, you should end up with a room full of fresh air, if you wait long enough to infinity. So find the formula for the concentration of CO2 in the room as a function of time. All right, well, it helps to have another variable. Let's let y be the amount of CO2 in the room. So if y is the actual amount in cubic feet, then the concentration of air in the room is just going to be y divided by the volume of the room, whatever that is. Now, we know that y is changing. So dy dt is going to be the incoming rate minus the outgoing rate. That's speaking very sloppily, but I want to get through this. The idea is we're pumping some CO2 in, we're letting some CO2 out. What's the rate at which it's coming in? Well, we have this flow rate and we have this concentration. So the incoming rate is F times Cn. The outgoing rate is going to be, well, we've got this flow and we've got this concentration. Oh, but wait, this one's constant. Concentration of CO2 in the incoming air is constant. It's fixed at 0.05%. But the room concentration is varying. That's Y over V. So this is F times Cn minus F times Y over V. Let's factor out the F. F times the quantity Cn minus Y over V. There's my differential equation, dy. So the modeling, we end up with a differential equation. Hey, is this quantity inside these parentheses a positive thing or a negative thing? Let's do this a different way. Let's do this as F times Cn minus C room. Think of it that way. That's how we got to here. Is this quantity inside parentheses a positive or negative thing? Marcy?
Negative.
Why?
Because air is leaving the room, and that's what Y prime is.
Well, air is coming into the room too.
Yeah. But, oh wait, no, it's I meant to say that the concentration of carbon dioxide is going down.
Right, the concentration of incoming air, CO2, is a low concentration. It's fresh air. The concentration of air in the room, of CO2 in the room is higher. We're trying to flush out that dirty air. So this is a negative quantity. So this is a negative quantity. I'd rather not deal with a negative quantity, so I'm going to do this. This is minus F times Y over V minus Cn. The reason I'm doing that is that I want my thing in parentheses to be a positive quantity. So dy dt is minus F times Y over V minus Cn. So let's separate and integrate. So we get dy times 1 over Y over V minus Cn equals F dt. So let's integrate both sides. So the integral of 1 over Y over V minus Cn dy equals the integral of F dt. This should be minus F. So when I do a U substitution, I end up with an extra factor of V that I've got to account for. So I'm going to skip ahead here because I want to finish this. I get ln of Y over, well, I want to make this a little bit simpler. No, that's right. ln of Y over V minus Cn, that's all in absolute values, equals minus Ft. F times T. So when I take E to both sides, I get E to the ln of the absolute value of Y over V minus Cn equals E to the minus Ft. And there should be a plus K here. And so there should be an E to the K here. K can be any real number, so E to the K can be any positive number. So I get Y minus V minus Cn equals E to the minus F times T, and I'm going to call this K, call this K1, this K1, call this K2. K2 can be any positive number. Any positive number. Okay, so add C in to both sides. Y over V equals C in. That's the concentration of CO2 in the incoming air. And then plus e to the minus ft times K2. But realize that what Y over V is the concentration of CO2 in the room. So we're kind of done here. So in other words, the concentration of CO2 in the room is going to be C for the incoming air plus this thing, e to the minus ft times K2. Now what is that K2? Well, we'd have to figure out we'd have to make the concentration match what it's supposed to match at time 0. At time 0, this concentration is supposed to be 0.15%. I can fix this. I can solve this. Notice what happens when time goes on and on and on towards infinity, kind of like this class. E to the minus ft gets closer and closer to 0. This term becomes closer and closer to 0, and the concentration becomes the concentration of the incoming air. So it's pretty cool. But let's fix the constants. Let's get the value for K2. So we know that at time 0, we have to have the concentration of air in the room must be 0.15%. So we know that 0.15% has to equal 0.05% plus e to the 0 times K2. So that's just 0.05% plus K2. So that tells us that K2 has to be 0.1. So that tells us that the concentration of CO2 in the room as a function of time is going to be the concentration in the incoming air, so 0.05% plus 0.1% e to the minus 2 meters, minus 2 times t. So again, initially, when this is 0, this is 1, my concentration is 0.15. As time goes on, this becomes 0. That kills this whole term, and that makes the concentration go down to the room to the concentration for the incoming air. So it's messy, but it's a cool problem because it's another modeling problem. It's very different from the logistic growth that we had last week. All right, thank you everybody. Andrew, you came in. Let me see who else.